The graphical form of our probability mass functions and cumulative distribution functions can often reveal very important information about what's going on with our random variable, and particularly in terms of where it might be centered and in some sense of the measure of spread. So it's always important and valuable to get a visual image of our distribution. And so what we had looked at before with the pedestrian crossing example was a probability mass function where for our 5 different possible outcomes we had the probability masses of 1/9, 2/9, and 3/9, and then 0 for all the other time values, whether those be real numbers or outside of the 3, 6, 9, 12, and 15. And the sort of subtleties and precision and accuracy of how you represent these graphically are that when we go to plot, for instance, the probability mass associated with Ti equal to 3 or 15, it being 1/9, rather than just put a stick there or a dot at the 1/9 value, what we do is we actually make that a lollipop to emphasize that that's a probability mass, a discrete random variable that we're considering. And so for the others here, then of 2/9 and 3/9, we have a probability mass lollipop at 6 and 12 of 2/9 high, and then at 9 we have then the 3/9. And it's very apparent immediately when we look at the probability mass function in this graphical form that the distribution is symmetric about this middle point, and that middle point being 9. We'll find out that that is also a centroid and also what we will call the mean of this particular random variable. Right? When we look at the CDF, right, remember that is just the probability that t, a random variable, is less than or equal to t sub I. Then the probability that it's less than or equal to 3, and I'm going to change the scale here on you, and note that we can never have a total probability more than 1. So I've got our scale at about not quite half of what we had before. Right? And so for 3, then that's going to be 1/9, which will be sitting right about here. And again, we're going to go ahead and use the little lollipop kind of model to start off with. There's no chance or 0 chance that we're down here. Right now we go up to probability that we're less than or equal to 6, and so we add 1/9 and 2/9, and we have 3/9, or 0.33. And so we need to end up right here, but how do we get there? And note that there's no probability mass between 3 and 6. So this is a straight line, and then as soon as we get to 6, we immediately jump up. Right, so it's kind of a version of the lollipop, except for how we're stacking things here. Okay, so from 1/9, and obviously I didn't draw this perfectly to scale here on the first one. So we have 1/9 here and 3/9 right there, or 0.33 there. And then as we go over to 9, we're going to add another then 3/9 on top of that. So we'll be up at 0.67. And again, we're going to go over flat until we get to 9 and then immediately jump up. When we're right exactly at 9, that includes the possibility of 9. So that's where we add the lumped mass of 3/9 to get up to 0.67. And then finally we come over to 12 flat, go up another 2/9 or 8/9 total. And then when we come over to 15, we then jump up the last 1/9 to exactly 1.0. And so for a discrete random variable, one way that you can tell if someone just gave you a CDF and they didn't tell you whether it was a discrete or a continuous random variable, you know it's discrete if you've got this stair-step CDF. You also know that there's going to be something incorrect about the CDF if, as we march out to larger values of the random variable, somehow we end up with a decrease in the CDF. That's not actually possible. Right? So they've made a mistake. And in a sense, if you have a negative slope this was decreasing somehow, then you have an improperly defined CDF. Right? That would suggest that somehow you had negative probability. So again, the graphical form can be very helpful in trying to understand what's going on with the random variable. And we're going to get into this notion of, well, where's the centroid or center of the body of this probability mass? Here it's very obvious where it's located, but if it's not so obvious, how might we locate it? And how do we measure how far spread out this is away from that centroid? Both of those concepts are coming up next.